Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Rocket Monday, let's talk about roll out solar array. So let's dive right into it. Now, what's the problem with a normal solar system that we are talking about roll-out system? Well, near-Earth missions, basically missions that are like basically inside Mars, so to say, generally require a lot of power. Specifically, like lower satellites, they need a lot of power to stay afloat. Basically, they want to use iron engines that consume a lot of power, so they need a lot of power. Thankfully, solar is a good and reliable option. However, you need panels that are huge. And recently, you must have seen a trend of panels that are like this, origami-inspired panels where they just unfurl and things of that nature. And mounting systems of their cells, basically cells have to be mounted in panels and panel have to be mounted on satellites or space station, whatever have you. Those mechanisms are becoming the limiting factor at this point in time. They were not a very big issue in early days, but nowadays that's a very big limiting factor. And deploying in space is such a big deal. Like if you had this sort of animation, which I can guarantee you, even NASA was pursuing it, the moment you send this animation to like engineers, like, can you build this, they were like no. And even this sort of mechanism that is actually used in Russian systems and Chinese system, even this mechanism, they are expensive, they are fragile, they are complicated, and they have a lot of issues. Meaning you don't think about that. It's like when we are talking about satellites, they mean like, okay, what is the resolution of main camera, what is the antenna gain and things of that nature. But like one of the limiting factor is the solar cell. And there is another issue with solar cells. It's like if you need huge cells, meaning let's say you are trying to build a space station, you hit up with another system. It's not that heavy. Let me be very clear, they are not heavy, but they are big, meaning their volumetric packing efficiency, meaning how many liters you need to pack it, it's very high. And you must have noticed that European Space Agency uses something that has huge fairings, meaning the rocket is not that powerful. It's almost same power as like Falcon 9 or even less, but somehow it has huge fairing. Why? Well, we have reached a point where our rockets are far more powerful, but volume is the limiting factor, meaning how many liters of space you have is the issue. These panels, they are inherently very inefficient in packing. Not only your weight will go up, your height will go up, okay, you can manage that. Your width will go up, okay, now you need to diameter, everything, length, width, height, all will grow up. So that creates a inherent limitation how big of a panel you can pack into the system. So that's a serious problem. So roll-out solar system is supposed to solve that issue. Basically, normal systems have too many small parts, meaning if you look at, let's say this is a panel view when ISS was deploying a solar cell, you're like, okay, why there is a giant hole here? Well, you have to understand there are many parts in solar cell deployment. Even like something like ISS, it was a very complicated mechanism to have packing efficiency which they wanted to achieve. It was achieved by a lot of complicated things. It had guide wires, it had safety wires, things of that nature. One of the guide wires snagged and almost tear the panel apart. Like literally this had to be fixed by actual spacewalk. So understand this is a common thing that happens with many satellites. There are many actual real life satellites that have either lost power simply because, like, let's say they had two arrays, one array did not deploy, or they had a scenario where the array failed to open. So that's one of those things that you do not think about, but it's a serious hazard to any mission. So that's why people want to remove, where it's like, okay, you have 10 hinges, how about you only have one thing? It's much easier to make sure that one thing always works rather than like having 10 things that always works. So that's a serious limitation. You want to remove parts. The more parts you remove, the better it becomes. Now what they are trying to achieve, basically this puppy is basically having tape measure. Now this sort of technology, now if you open the tape measure, basically this part, you will find there are two coils. One coil is the spring, second is this system. Now if you roll the blade part of it, basically the part that you use to measure, you will notice that if you let it go, it straightens up. Now again, I'm not rolling it because of the spin. If I rolled it, it's like it might snap back. So even if you roll it like this, it will open like that. Now, so somebody came up with the idea. Of course, they tested it with a toilet paper and this system, and then they realized composite fiber matrix system, where the blade was, instead of made out of steel, was made out of composite fiber. Videos have been provided down below, and they do also have dampeners, so it does not go pachang. It goes very slowly. So that was the idea. Now, okay, that's the support structure that you see on this side. Those are support structure. What about the cell itself? Now, cell is kind of flexible. Now, be mindful. I am talking about a panel is being flexible, not the cell. The cell itself is rigid, as in like it's a what we call tri-junction gallium cells. They are very efficient, meaning they can cross 30% in terms of efficiency. Normal cells only go to 20% in real world use. That's supposed to be 30+% in real world. So that's the idea behind it. And all they have is like cells are there, and the bonding wire that is connecting both of them, they are flexible. So inherently, it's just tied together in like a cloth kind of structure. So it's a very flexible. So this cell itself will not bend, but the joints between the cell, they will bend. So that gives you a, in large enough structure that behaves like completely like flexible, almost like a cloth. So cloth would be tensioned utilizing those two black struts, meaning the tension structure that you see here. Basically in ISS, this would be the truss structure would be there, and in case of this system, this will be the tensioning, because without tensioning it will just flap around. And you might be like, why would we flap around in space? Well, things move in space. For example, your gyroscopes. So, or in case of space station, people in the space station, so they need something to tension it with, and dampness is there to make sure that it does not go fachang. And like the person showed the demo, real world, real scale demo, like which is actually in the space station right now, and he was just open it, is like whoosh, it opened. It's like, of course we make sure that there are dampness, so it does not open that quickly. I'm pretty sure if it did that, it will have much bigger issues than this. So that was the idea, and it has been actually tested out. So first test that was carried out this puppy was SpaceX by CRS, Commercial Resupply Mission 11 number 3 July 2017. Now this is one of those things that I saw almost in real time, meaning when they were actually launching this thing. And what they were actually testing for is basically vibration characteristics. Think of it this way: things like satellite, space station, they have a lot of moving parts. For example, if you have talking about even Hubble, you will have a focusing system. You could have systems that are like gyroscopes that will move systems. So there are a lot of things that introduce motion. Now if you are talking about a rigid body, like let's say I'm the satellite body, I'm the rigid body, everything is fine. Now here's the deal: you have an extended panel like this. Now I move even a little bit, the panel moves a lot, so that will create oscillation. Now that is something that you have to understand before you send it to space, because if you do not know about this, like let's say your satellite directly bought this and installed it and send it up there, if you do not know how they are behaving, how it's gonna, like, what frequency it has to oscillate, how long it takes to dampen it down, your gyroscope will literally self-destruct the satellite, because it will not know what to do. It's like, dude, something is vibrating, I'm not in the correct orientation. It's like it needs to know, okay, I moved it like, let's say 5 degrees, I'm gonna take some time, then I'm gonna slowly correct it, so it, like, oscillation goes down. So for when they were testing this puppy out, on the base of this unit, basically base unit, they had giant motors with vibrators, basically vibrating throughout all the frequencies, basically 10 kilohertz, 20 kilohertz. Like how do you test a 3D printer? Basically by moving it very rapidly. Same thing they were done to make sure they know the entire vibration characteristics, so they can sell it to basically satellite manufacturers, like, hey, use this, and they can like program that data point into their control software, where it's like, I got this, I can manage it. Without that control data point, your satellite is lol. Then another issue is, because of the material, it may look like a balloon that is being inflated, especially in this sort of system. Trust me, it's not. That's why I would urge you to check that video down below. Real world scale, it's like, it almost looks weird, but people who have worked with this system will know. So the idea with this thing is, because it's so thin composite material, the total mass of it is very light, meaning few grams or even barely a few kilos, even on large panels. So side effect of that is it will heat up very quickly, and again it's of a dark color, so it will heat up very quickly. Problem is, if you are going through the like ludicrously scorching solar radiation on the day side, what happens when you go into Earth's shadow? Now you are exposed to very cold, meaning you are radiatively losing energy, but there's no buffer, there is no atmosphere. So that shock going from very high heat to almost losing all that energy very quickly will create thermal shocks. Now that shock in some scenarios acts as a physical shock, meaning your things will physically move, like doing. Springs can literally contract and all that. So that also had to be tested. So that's why they had to have this outside the space station. Another aspect which they said is like many of the solar panels that we built on Earth, basically for satellites, they're overbuilt. Why? The only way to test that is you have to test it either with support structure, which you cannot guarantee. If you are using support structure and you remove that, you do not have any guarantee that this puppy will work in space. And if you add those space structure, you basically make your panels bulky, so that creates another issue. So that's why they also had to test that part. It's like on their mathematics, they're like, everything is awesome. They tested it with using support structure, but still worked in space because it has less part. You know for a fact that this puppy will work. Inherently, there is not too much hoo-ha into this, so it will work. And the high temperature delta, that also was another aspect. Can it actually survive? How much oscillation it induces due to thermal stress, due to basically oscillation amplification, things of that nature. So testing was done successfully. Everything they wanted to know, they figured it out. They even had a lot of dot metrics placed on there, and they had 2 cameras. So that utilizing 2 cameras, they could know the 3D location, and they'll know how it's vibrating and all that jazz. Everything worked out. However, they wanted to close it up, then pack it into return capsule, and then just burn it in the atmosphere. That closing mechanism failed. Now again, that's not an issue in any satellite. They may not even have closing mechanism in satellites, so what's the point? So that's not considered as a failure. They just detached it. Now because of the huge surface area and comparatively lightweight, it took a very long time to crash into Earth. I think some people are suggesting around 5 months would have taken to do that. So it was detached, and this was conclusion of the mission of testing this phase. So now we come to ISS. Now ISS legacy panels, basically the panels that you see behind it, they're old, meaning they were built with a 20-year-old technology with a service expected life of 15 years. So you will like, wait a minute, that means they are literally out of warranty? Yes, they are. So that's why the replacement was rushed into service very quickly. So this panel is smaller than that, but it has higher quality cells, meaning that tri-junction cells that are utilizing gallium based system is supposed to give higher efficiencies, and comparatively speaking is much smaller and much more powerful. So it's not like, okay, it's smaller and like, you know, it's just smaller. No, it's smaller and more powerful, so it's double benefit on that. And replacement was done in such a way that it will mount on literally on the same spot where the panels have been mounted, the old panel. Now you're like, why do you want to do that? Well, reality is the panels have very complex control mechanism, meaning the panels have been designed in such a way they can rotate in such a way so sun can be facing them completely, and when they are in the dark side they align to the basically direction vector. Basically if the space station is moving, the cells will be arranged like this. They will not be like this, because doing this, that will create atmospheric drag. It will need much more propellant to boost it up again. So there is a very complex control mechanism on the base of each of this solar system. So utilizing the base itself, they are mounting the panel right there. And that the main reason why anybody wanted to do this compact packing efficiency. It took like one of these panels took almost an entire mission, as in like entire space shuttle mission, versus this where you had the whole system plus the solar panel, like a whole capsule plus the solar panel. It's like GG. And you can see that like if basically Falcon 9 was used just as a deployment mission, it's like, you know, just transport it to basically low Earth orbit where other system will grab it. They would not even needed that folding mechanism. They just folded it once, but like they would not even need that. They will just have long rolls of it. So you can get that point. Like compare this sort of simplicity versus what was used with ISS. It's like night and day. Like this is something you can close your eye and trust on. Like this is the full scale of it. It's rather small, so to say. And this was a testing mechanism where they had clamps to make sure. Be mindful, if you are designing a solar panel, you have to design it for space, not for Earth, because if you design it for Earth, it will work. We have solar panels on Earth. Issue is it will be way too overweight. So this was done on ISS and it's already been tested successfully, and they will soon replace like at least basically 6 of the system will be replacing the old one. 2 of that legacy will be left. You do not want to overpower also. So this is very successful at this point in time. So what we can expect in the future, because this is something going on right now, meaning only 1 or 2 units have been deployed, and by the time you're watching this video, you could have a news like, you know, 4th or last module has been attached. So it's still a very recent thing. So what we can expect in the future is basically another big mission is DART mission. Now this puppy is supposed to use ion engines, meaning it needs a lot of energy, and they realized very early on is that those origami system, you know, you can pack and all that, yeah, it's an engineering nightmare. It has too many things to go wrong. This system is rather inherently simple, and this puppy is supposed to be even more powerful than one of those panels, as in like 20 kilowatt system. This puppy is supposed to be around 25 kilowatt. So it's a big system. And that mission already planned, meaning the cells have already been built, panels have already been built and tested. So things are going along for that mission. And right now more improvements in the cell technology, because you have to understand, military will want to pay very high prices for, rather than like, you know, tri-junction, they may want to go for quad junction or some things that are using very expensive metal like iridium and things of that nature. You can achieve 50% efficiency. Now why would military want to do that? Well, the military satellite is supposed to be stealth, meaning they should not scream like, look at me. So how do you make sure that it's not screaming look at me in radar? Make the solar panel small, because that's the biggest thing that, you know, stands out. So making a cell with higher higher energy efficiency is the easiest way to achieve that, and having this structure allows them to. And then in those sort of scenario, I could say that if they are like changing the orbit and they want to be like completely stealth, they could roll the solar panel inside. If they have enough batteries, they can do that. So that's why better cells will allow even more energy and bigger panels, because be mindful, what ISS did was like a very step 1 kind of scenario. Company that is working on this, and they're planning for huge arrays, meaning huge arrays that are lightweight enough that it can inherently be used with basically ion engine transport for Mars. Right now we cannot go to Mars as in like human mission. You can do that, but problem is you do not want to do that, or you should not do that simply because it will take many months. You want to travel time within a month. That can be done. So that's why this sort of panel structure is very critical. It may look like a small thing, who cares about a better panel structure? No, that matters a lot. Inherently, like ISS were like almost doomed from the day 1 when they were trying to unfold the panel. That's a very serious one. Like when you watch animations of NASA and all that, it's like, oh, yeah, That's not how real works engineering works. It's like it's very difficult. So this sort of system that can simplify and give you a peace of mind. It's like, no, if you're building a, let's say, giant space farm, if you're building a, let's say, lunar base, they are also planning for that, because lunar gravity is so low that this puppy will work without any change, so to say. So a lot of things can be done, bigger panels, anything can be done, and power hungry missions will become open. And like you can see that, like, that's how small the system is. Like, these are the two astronauts. So fundamentally speaking, there are a lot of scope opened up because of this technology. If this technology is proven successful, because this puppy will be far more dynamically active, meaning it will be moving, engine thrusting, orbiting, things of that nature. So it will do a lot of those things if this structure survives that. As in, like, oscillations is one thing to have test oscillation versus real world have been used in, like, multiple scenarios kind of test data. If they survive this, I'm pretty sure literally overnight every company will be like, okay, give me one of those. They're like, shut up, take my money, give me one of those. So this was my presentation on roll-on solar array. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment, because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.